So we left off, we talked about single or monoalphabetic ciphers. Caesar cipher. We talked about that last time. Talked about index coincidence, and we said we're going to start talking about polyalphabetic ciphers. That's where we are now. Okay? Polyalphabetic means multiple alphabets. Okay? So we have a single alphabet. We talked about the index of coincidence ends up being 0.0667. Okay? With a multiple alphabets, you basically flatten the distribution. We'll see how that works. Okay? So if we use one alphabet, okay, so in other words, we have just one single alphabet, that's where we get 0.667. 0.0667. Two alphabets, three alphabets, and so on and so forth. And infinity alphabets, we actually get a different index of coincidence. Because remember we learned that in English, what's the most popular letter? E. E. We learned E is the most popular letter. So what if there was no popular letter? What if all letters had an equal distribution? Would that be harder to figure out stuff? Oh, most definitely. That's what this does for us. Okay? All right. So the way that the example is, so we have our plain text here at the top. This is a test XXXX. First of all, why do I have the 4 X's on there? Anybody?
To make it visible to 5.
Make it visible to 5 to complete the group. Remember, well, some of you are probably too young to remember, but when I was a kid, on the Sunday paper, they had that thing where, you know, you'd solve the 2-letter ones first, and then you go to the 3-letter one. What was that? The Deadly Jumble or something, wherever the heck that was. Scramble or something. Well, it was easy because we started with the short ones. It was either what? At, is, of, and that was about it. But now we don't know that anymore. So we added a component to make it tougher already, just by breaking it in groups of 5. Okay? So the way this works is, so if we encrypt the first letter with our first alphabet, okay, the second letter with the second alphabet, because remember, the first alphabet, maybe E is the most popular letter. Yes?
The first alphabet is the alphabet
Shifted by 1.
Shifted by 1. The
Right.
second alphabet is the alphabet.
Shifted by 2.
That alphabet shifted
By 2.
by 2, so it actually makes the first alphabet shifted by 3.
No, it's one more. So
One more.
So one more each time
Right.
instead of, okay.
You know, if you worked on the assignment, some of you were done already, it's shifted by 3. So A becomes D, it's shifted by 3. Well, what if we shift by 1, the second letter we shift by 2, the third letter we shift by 3, the fourth letter we shift by 1 again, so we're no longer going to be able to go with E is the most popular letter anymore, because they're not shifted with the same alphabet. Okay? Everybody okay?
So a shift according to the previous.
It's shifted according to basically the key, and we're going to see what the key comes into play here in a second. That's what the Kaczynski method does, is determine the key length for us. Okay? So we can actually use more alphabets even, up to 26 different alphabets, because that's what English has, is 26 different letters. Okay? All right. The Vigenere cipher, or as the guy who taught me in Atlanta, the Vigenere. It's not Vigenere. I was laughing. Did I tell you the story already? I was at a CISSP boot camp class. That's where they teach, you know, all the cybersecurity classes we have here at Rose State. Take all of those classes and put them into 1 week. Because the CISSP is the civilian equivalent of the CNSS certifications. It covers everything, but only half an inch deep. Literally everything, but no depth. It's like they ask you one question about this and one question about this. So it's really just a touch on everything. But the guy goes, yes, and there's this multiple alphabet cipher called the Vigenere. I'm like, what? It's just the Vigenere. I'm like, I'm assuming you mean the Vigenere cipher. Okay, what he said. It was like, wow, it was pretty fun. Okay. It's a polyalphabetic cipher, which means a multiple alphabet cipher based on the Vigenere tableau or Vigenere table. Okay? It has 26 possible alphabets, each keyed by a letter. Okay? So, we have our plain text, but so for what the con of man or whatever that stupid saying is. Okay? So the B will encrypt with the J alphabet. The U will encrypt with the U alphabet. The T will encrypt with the L alphabet. The S will encrypt with the I alphabet, and so on and so forth. But you see, Juliet, Juliet, Juliet keeps repeating. So how long is our key in this example? 6. 1, 2, 3, 4, 5, 6. Then the key repeats again. So imagine doing that first assignment, where right now it's everything shifted by 3. Okay? What if every letter was shifted by a different value? That's what this is. It's exactly what this is. Because if you guys shifted by 3, the whole thing turns into English. But what if every six, the first 6 were shifted to different values, and then they repeated. So this one, the B is shifted by 1, the U is shifted by 18, the T is shifted by 5. Can you imagine how hard that would be? It was considered unbreakable for 300 years. I mean, if you compare what we learned with our first assignment and this one, yeah, it's definitely much different, much tougher. Okay. But based on the plain text in the key, which we're going to see in a second, we get the ciphertext. I'm going to write on the board, which means I have to roll up the screen. I think it's on the next page. Yeah, okay. I'm going to write a couple of these here. I'm going to go, so, J, B, U, U, L, T, I, S, E, 0. Okay? We're just going to do 5. Okay?
Not 0, O.
Well, I don't have any
There's no
numbers.
numbers.
I don't have any numbers here. So this is what it looks like. Okay? So if I was to take B, take B and go down to J, I get a K. Y'all agree? So if I took B at the top, went down to J on the left side, they meet a K. Everybody okay with that? So this is our plain text, this is our key, our ciphertext. So the key is K, the plain text is B. Actually, the way we're doing this, I'm sorry, the key is J. The left side will be the key. The top part will be the plain text. And the middle will be the ciphertext, okay? So if we took the key J along with the plain text B, we end up with K. Everybody see that? So if I take the key U and the plain text U, O. Should be O, isn't it? Okay. I end up with O. Okay? I'm just going along till they match. So I had K, O. Okay, so the key L, the plain text T, E. So the key L, plain text T, ciphertext E. Okay, let's do 2 more. Key I, plain text S, ciphertext A. Everybody with me? Mm-hmm. Okay. Key E, plain text O. So key E, plain text O, ciphertext S. Okay. Now let's go back one and see if we did that right. K-E-O-A-S. Everybody see how I did that? Everybody following along? How hard is that to do? Now, if you're looking at these, okay, like this, really the first alphabet here is shifted by nothing. A is A. The second column, A is shifted by 1, A is shifted by 2, A is shifted by 3, 4, 5, 6. So when you guys did that assignment, 1, 2, 3, you actually did the entire thing based on that alphabet. The assignment 1 was shifted based on the D alphabet, which is a 3. So everybody following along at how this works? So is it a lot tougher to do? It's not hard to do now that you know how it works. But the problem is, how do you know what the key is? Okay? All right. So we all...
My next question,
What?
how do you find the key?
Well, we're going to get there. Okay. How do we get to break this darn thing? Okay, the Vigenere cipher, or Vigenere-like substitution ciphers. Can you see okay with the board up or down? Does it matter? Down's better? All right, let me stop this. Okay. Vigenere-like substitution ciphers were regarded as many as practically unbreakable for 300 years. Okay? What does practically unbreakable means? It might take a long time. I mean, think back to Caesar days, Julius Caesar days. What did they have? They had skirts, swords, and chariots. Isn't that about what they had? They had what? They had abacuses, okay. But they really didn't have a lot of computers. I don't think they had iPads yet. No calculators. I mean, again, they had abacuses. But there really wasn't a lot of technology around. There really wasn't a lot of anything. So, you know, for someone to actually come up with this is like, oh my God, amazing. Okay? It's crazy stuff. Okay? In 1863, a Prussian major called Kaczynski. Where's this guy from? Prussia. What rank was he? Major. What was his last name? So if I asked where this guy came from, you could tell me?
No.
Prussia, you'd probably say his name was? There you go. You got probably 2 test questions there. Okay. He proposed the method. Actually, when did he do it? Now, it wasn't 1683 or 1963. It was 1863. Okay, there's certain things I'm covering a little more in detail. What was his name again? What year did he? Okay. If you get my point here, okay? Certain things you might want to know. Okay, so in 1863, that was 1863, okay, a Prussian major named Kaczynski proposed the method for breaking this Vigenere cipher. Okay, he said it consisted of finding the length of the keyword and then dividing the messages into the simple substitution ciphers. So, we know after the first assignment that if everything is shifted the same way, it's pretty simple, isn't it? So what if we could figure out that our key is like, say, 5 or 6? Was it 6 on the one we did? 6? Mm-hmm. So that means the first one and the 7th one are shifted with the same value. Is that correct? Mm-hmm. So it's first one, 7th one, and what, the 13th one? Am I right?
Yes.
1, 7, and 13 are all shifted the same. So if I could pick out every 6th character and work on just those, couldn't I then take those and figure out what's the most common letter amongst every 6th character, the most common letter replaced with an E, and do it like it was a simple substitution cipher? And then work on number 2, and number 8, and number 14. You know, so I'm basically making 6 simple substitution ciphers. You understand what I'm saying? Okay. So we're going to figure out, because it's finding the length of the keyword and then dividing it up into a whole bunch of small substitution ciphers. So, to make this cipher better, would it be better to have a short key length or a long key length? Oh, long, definitely. So I mean, if our key was 2 in length, well, we have 2 whole alphabets to worry about. So every other one we work on, and so the longer the key, the better. Okay. Then we can use frequency analysis to solve the resulting. So again, we took number 1 and number 7 and number 13 and every 6 characters, took all those together, looked for the most common letter, replace it with E. The second most common letter, replace it with an R, an A, or whatever the heck it is, and whatever it is in English. Then we work on the 2nd and the 8th and the 14th. Then we work on the 3rd, the 9th, and the 15th, and so on and so forth. Everybody follow me along here? And we would use what's called frequency analysis to see what the most common letter is. Okay? Now, I actually wrote a program to do that, and it's not quite finished, but it's close. I have quite a few programs that are close. Problem is, I was writing these, and it's like, okay, next week I can cover a new topic, so I got to write a new program, and I never quite... I wrote a program to solve AES, and it's all the way down to the Claude field, which you'll learn about. Right at the end, I just never finished it. Maybe someday I'll do it. I just always got something coming up. But so far, so good. What was his last name again? When was he born? Okay. Any of you get that wrong, you just quit. Go drop your classes. Okay. All right. So how does this work? To break a polyalphabetic cipher system, the Gazisi's method, here's how it works. Okay. First of all, identify a repeating pattern or 3 or more letters. Now, that number one statement causes more issues than any other issues on all of this. Let me explain why. I said 3 or more. So if you had a choice between a repeating pattern of 3 or the repeating pattern of 12, which one are you going to pick? 12. The longer the repeat, the better. Okay? You'll see why in a second. You want to have the longest repeating string. Because the odds are that 3 letters next to each other, it's like THE, can be used quite a bit through our paper, through our document, whatever we're encrypting or something. So, but if you could get, something that's 12 letters long, then that's a big old long string to work with. So look for the longest one. Don't just use something with 3, because you'll come back with, oh, it repeated, 92 times, and you can be doing a lot more math than you need to do. Okay? So, for each pattern, for each repeating pattern, write down the starting position. Again, I'm going to show you this. Write down the starting position. Where does the repeating pattern start? Okay? So for each of the repeats, write down the starting position all throughout your document. Okay, it starts at 12, it starts at 27, it starts at 82, and it starts at 106. So I wrote down all the starting positions. So far, so good? Okay? Then compute the differences between them. So the first one started at 12, the second one started at 86, so I subtract the difference and I get some number. I'm not a mathematician. Whatever that comes up to be. Okay? So I go from each starting position, subtract the difference, and keep track of the differences. So I go from the starting position of repeat pattern 1 to starting position repeat pattern 2, and write that number down. Subtract the 2, write it down. Then go from 2 to 3, write that one down. And 3 to 4, write that one down, so on and so forth. Y'all with me? Okay. Then determine the factors of them. Now we're going to do some tough math here. If I give you the number 6, what are the factors of 6?
2, 3, 6, 2, 3.
1, 2, 3, 6. What's the factors of 7? 1 and 7. What's the factors of 10?
2, 5,
1, 2, 5, and 10. Now 1 is probably not the key length. I mean, if you have a key length of 1, we're pretty much talking the Caesar cipher here. Okay? So 1 is probably not what you're looking for. Okay? But, so you understand what factoring is. Take the numbers, get all the factors of each one. So you took the starting position of 2, starting position 1, starting position 2, subtracted them, got a number. Factor that number. Not the starting positions, factor the difference. Okay? Then do the same from 2 to 3. Get that difference, factor those numbers out. So I said, determine all the factors for the differences. The key length will be one of the factors that appears most often. So I see 2, 3, and 5 quite frequently. So my answer would be 2, 3, and 5. Probably 5. But the correct answer to the homework would be 2, 3, and 5. Everyone with me? Mm-hmm. For the homework, I want to see the starting positions, the differences, the factors, and then the common factors and what you think the answer is. Okay? Don't just tell me the key's Bob. Because literally, there's websites out there, you plug this homework in, boom, tells you the answer in a second. That's fine. But you know that whole thing back in math, show your work? They're not going to show the work. Okay? So once you get the key length, partition and see if the same index sequences is for English. In other words, do the frequency analysis. Don't have to do that part. Only have to do says 1 through 5. Okay? All right, here's an example. I actually edited it. This is the first semester this example has ever been seen. Don't you feel like special here?
A little bit.
First semester. I've been talking about fixing it for 5 years now. I fixed it this year. Okay. So I have my key, I have my plain text, and my cipher text. Now, looking at this, okay, so can you tell me that if I see this, the key of NS, actually, you can see the key is Dickens. Everybody see that? Hopefully you see that. And by the way, the phrase Dickens, yeah, the key is Nsdick. Okay, the plain text is actually, it was the best of times, it was the worst of times, so on and so forth, from A Tale of Two Cities. That's what our plain text is, okay? Just showing you that this actually works. And what really sucked, when I was doing this, I was adding the ciphertext line, because I didn't have that on there before. And it didn't work. I was like, what the heck? Well, the problem was when I was copying the text in and pasting it into the thing to calculate it, I was putting a space in it. And it was obviously throwing it all off. But it was correct. But, okay, so if we took an N and an I, would we get a V every time?
Yeah.
Yeah, we always would. Because if we always use the key N, always use the key I, we would end up with the key V. So down here, NIV, NIV, so on and so forth. Everybody see that? So, and we're looking through this text for repeating strings. See, initially, well, I only showed the key and the plain text. But people didn't get the whole ciphertext thing. Because on your homework, I give you only the ciphertext. So if I gave you the key, I mean, I'm assuming if you all had this as your homework, you'd be like, oh, I'm guessing the key is Dickens. It'd be pretty simple. So I only give you the ciphertext. My point new for this year is you agree that if you have a certain plain text with the same, a certain ciphertext, you're going to get the same key. And you'll see that the repeating string is the same on each. Everybody see that? Because the whole point of Kaczynski is if you have enough text and that key is repeated enough, the same key is going to be under the same words in the text frequently enough. That's where he came up with. So, starting at the beginning, okay, 1, 2, 3, 4, 5, so on and so forth, you get to 20. Okay? Now, I will tell you when you're doing this assignment, I don't know what if you want to copy it out, because like Word will do word count for you and character count and all that stuff, watch the spaces. And I don't, did I give it to you in PDF or Word? Does anyone know?
Yeah.
Okay.
Yeah.
Be careful with the PDF. Sometimes when you highlight, it doesn't get all the characters. It's like you might highlight it and it leaves off the I at the end. Be very careful. If you have an issue, I'll try to put it up there in Word. I keep forgetting. But it's something about PDF. Sometimes when you copy a line, it doesn't get the, it might miss a character at the end or in the beginning or something. Okay. So, the first place we see this repeating string is at 20. So far, so good? The second place we see the repeating string is at 83. So, go ahead.
Is that 83 from 20?
83 from the beginning. From the beginning. Okay? So, then we go 83 and 20. Subtract the 2, the distance is 63. The factors of 63 are 3, 7, 9, 21, and 63. Okay? Then we keep looking. We find it again starting in position 104. The difference between 83 and 104 is 21. The factors are 3, 7, and 21. So what's our probable key length? 3, 7, or 21. In this case, it happens to be 7. Now, if we had more of this, if we took the entire Tale of Two Cities and encrypted the entire thing with Dickens, it would probably get down to one value. Okay? Yes, sir.
How did you assess it with 7?
I didn't. I just saw it.
Okay.
The correct answer for the homework would be it is either 2, 3, or 7.
Okay.
Because that are the repeating ones. Okay? It's normally the longer, but the correct answer would be 2, 3, or 7. That's going to be 100 points on that homework assignment. Okay. Is everybody okay with how this works? Okay. It's not difficult, but I want to see this math. Okay. I want to see the 20. Then I want to see 83. 83 minus 20 is 63. Factors of this. Then I want to see 104. 104 minus 83 is this. Factors of this. Yes, ma'am.
Do you want us to put the ciphertext into Word and highlight
You
what
can.
the repeating text is,
I
and
didn't do
then
that.
show?
I showed was the math.
Either way is fine. Actually, quite a few people do that. They highlight it, and then they do that and turn it in all different colors. I'm fine either way. I'm really just looking for the numbers. Okay? I think it's like 4 or 5 times. Does anyone know how many times it repeats? Does anyone finish it? 4?
Yeah.
It's 4? Okay, I think it's 4 times it repeats. Now, some people say, well, how can I possibly figure out? Actually, you know what? Let's leave that there for a second. Let's actually look at your homework assignment. There it is. How could you possibly find something repeating in there? Well, you can just highlight some of the letters and hit Find All in Word. That's one way to do it. But be careful with the spaces. Because right here is a space between S and G at the beginning. But over here, S and G might be together. So your best bet is to remove all the spaces. Okay? If you want it in Word, I can give it to you in Word. That way you can just search space, move, boom, done. And actually, if you have the newer Word, it'll automatically convert PDF to Word anyway. Okay? So, but it does repeat in there, and I can see it already because I know what it is. So. All right. Cheater. All right. So let's continue on. So far so good. Everybody with me here? Everybody understand how you will have to do this on multiple exams. And the ones on the exams are like this long. It's not like you're working off an entire page.
I'm not going to lie, that took me like an hour to find.
Yeah. Oh, it'll take you a little while. But you know the saying, for every 1 hour in class, how many hours are you supposed to be working on homework?
2.
It's 3 for every 1 hour in class. That's
Oh, we're supposed to do work on
doing this whole study thing. Okay. All right. Now let's talk about perfect substitution ciphers. Okay. Infinite non-repeating sequence of alphabets would be good. So instead of 26 alphabets, what if we had a never repeating key? Instead of Dickens, what if we used a book as the key? A book that was as long as the plain text. Can you imagine that? I want to get Carol the key. I say, oh, the Gideon's Bible, printed in 1992, starting on page 47. Wouldn't that be perfect? Because it's in every hotel room.
Yes, it is.
She can grab it, make sure it's the right edition, go to page 42, and boom, there's her key. One
Isn't
for
that
her.
what the CIA did?
Yeah, that's pretty much what. All right. There you go. All right. One-time pad. Again, a number that's used one time. It's a random number that's never reused, never repeats. It's just random. Okay? Or just say long random number sequence. Okay? Do y'all know there's no such thing as random? Do y'all know that? Random is always based on a seed. So, but there's no such thing as true random, even though it looks pretty much random. Okay. Or a Vernum cipher, which is punched paper tape. In other words, it's a very long tape that's non-repeating. Or a book cipher, like the Bible or the telephone book or something like that. So this stuff is immune to Kaczynski, because what are we looking for in Kaczynski? Repeating patterns. Well, if there's no repeating patterns, we're done. Like, the Kaczynski method will not work. Okay? All right. Or dual message entrapment. How about our messages? This message is crucial, yet the key we use is disregard this message. So you break it and you're like, great, which one's the right message? I broke it. Is this the message or is this the message? Is this the key or is this the key? I don't know which one to believe. So that's another way of doing it. Okay? Or transposition. So if I take the message, this is a message to show how transposition ciphers works XX. And I tell you, we decide on a column length of 10. So it becomes TSHOH. In other words, I'm reading down this way. Then I gotta tell you 10. Then you just put them all back together with the 10, and you're done. Because that's not gonna, because this method ain't gonna do that either. Okay? So far so good? Everybody with me? Okay. How can we break these? How can we break transposition ciphers? Looking for repeating stuff. Remember, just like we talked about in that Sunday paper, we look for the two letters or the THEs or the ANs and stuff like that. Look for repeating sets, then use a sliding window. Do it with 3, do it with 4, do it with 5. Just like you guys might have done the first assignment, shifted by 1, shifted by 2, shifted by 3. Well, shifted by 3. Doesn't make no sense to me. Shifted by 4. Still don't, and keep going until you get one that actually works. That's all. Now again, if the column width was 682, that would suck. But if the column width was 10, I mean, we're almost halfway done here already. So it'll be pretty easy. Okay? All right. Again, we talked about the sliding window, which I just showed. I'm not going to walk through it, but okay. Or we could use double columnar. Man, that word's tough. Okay, double columnar transposition. Maybe we did it with 10, then takes that text and do it with 15. So do it with 10, just like you saw. Then take that result and do it again with 15. So we'll have to decrypt it with 15, and then decrypt it with 10 before they actually get text. So you really couldn't use the sliding window because even if you slid it until you got to 15, it still doesn't make sense at 15. See what I'm saying? Okay. If I'm losing you, let me know. Okay. How can we break them? Okay. The relationship between the plain text and the ciphertext. The relationship is always important. Okay. You do not want to have a relationship between the plain text and the ciphertext. What I'm talking about is if I can change one character in the plain text and it changes one character in ciphertext, that's not a good thing. I mean, a specific character. You don't want that to happen. We'll talk more about that later. And here's the math behind it. You don't have to do that. Okay. I'm not going to require you to know this for the test. I'm not going to require you to have to do it on the test at all. Okay. Just know there are ways of doing it. Okay. Okay. How about if we combine two or more approaches? So we take our plain text, encrypt it with a key. Then take that ciphertext and encrypt it with a different key. What do you think about that? That's pretty good. It's kind of like having 2 locks on your house. Okay? If they only have one key, they're screwed because they need both keys to get in. It's what, I used to teach the networking classes for a long time. If you know anything about networking, you know you can have share permissions and then file level permissions. Does it really matter if you set share permissions? Well, if you always set file permissions, who cares about the share permissions? It's kind of like a screen door of your house. My screen door of my house, the lock broke years ago. Do I fix it? Why? I mean, it's just a screen door.
Keeps the flies out.
Keep the flies out, and it doesn't have to be locked for that. So my point is, even if I lock this, if the screen door is unlocked, as long as I always lock the inside door, I'm good. Okay? So.
But if somebody goes to break into your house, they only have to go through one lock, and if you lock.
Yeah, they don't have to go through a screen door. Actually, one day the lock screwed up and I couldn't open the darn thing. Basically, I had one where you push down and the thing, it wouldn't slide over. So I had to get the old screwdriver and pry it open. I just removed the lock. And it's... All right. Shannon's characteristics. If you wanted to know another slide that would be very beneficial on your upcoming exam, this would probably be a good one. Okay. So Shannon wrote a book called The Characteristics of Good Ciphers. He wrote it in 1949. It says the amount of secrecy needed should determine the amount of effort needed for encryption and decryption. In other words, timeliness. So if I am encrypting the pizza order, or I'm encrypting the nuclear launch codes, I'm thinking they really don't need to be encrypted in the same way. Unless it's the pizza order for the day they're making wasn't the Iraq war or something? Everybody went to Pentagon and they ordered like more pizzas than ever, and then you found out that they only do that on days when they declare war. Did y'all see that news article a few years back? They were saying that the number of pizza orders the day before, I think it was the Persian Gulf War, was the highest it had been since the previous time they declared a war, or something like that.
For deliveries to the White House?
For deliveries to the Pentagon and the White House and stuff. Yeah.
Wow.
Because so many people were there. They said there was a direct correlation between that. So it's, yeah.
For an extensive time.
So, principles of timeliness. If I'm going to encrypt something that really doesn't matter, why worry? Why would I spend as much time? Okay. Keys and ciphering algorithms should be key free from complexity. DES, which we will learn, is very complex. Well, considering it was made in the 70s, yes, it was very complex. Okay? And to this day, they still don't know why some of the stuff was done. They're like, why did they do that? No one really knows. They found that just because it's confusing doesn't mean it's good. Okay, that's literally what they proved. AES, which we will learn in here, was based on an open worldwide competition. The entire algorithm is open source. We are literally going to show the entire algorithm in this class. It's still a good algorithm, but it's not secret. They learned that just because it's secret doesn't mean it's good. That's also, you can also think about the whole open or off-the-shelf software versus open source software, that kind of thing. So Microsoft is secret code, Linux is off-the-shelf or open source. Is Microsoft really that much better? In some aspects, but Linux is better in some aspects as well. So the whole point is, keys and the algorithms they use should be free from complexity. Okay? Implementation should be as simple as possible. Why is that important? Well, we're going to get everybody and their brother to use our new algorithm. We're going to have it embedded in cell phones and toasters and everything. Okay? And if it's really complex, what happens? People screw it up. You want it so it's very easy to implement. Okay? Errors should not propagate and corrupt the message. Can you imagine if you're sending the shoes message through and there's one screw up at the very beginning? The entire rest of the Encyclopedia Britannica is in Chinese or something. That wouldn't be good. You'll learn when we get to block ciphers that yes, it will corrupt that block, but just that block. If you know anything about networking, you should have learned that we break our messages into packets. Why do we do that? Well, if one packet gets lost or corrupt, what do we have to repeat? The entire blooming thing? No, just that one. It's like you go to the grocery store, you drop the bag with eggs in it. You didn't drop the bag with everything else in it, so what do I need to replace? The bag with the eggs in it, that's it. So you don't want the errors to propagate through the entire message. Ciphertext size should be equal to or smaller than plain text size. We don't want to take a plain text that's 5 pages long and end up with a ciphertext that's 8,000 pages long, because that will get exponentially larger. You want it to be equal to or smaller. Okay? So far, so good? This is what Shannon had to say, by the way. Okay. All right. Trustworthy encryption systems are normally based on sound math. Okay? I'm not a mathematician. I can do basic math. I've been up through calculus, but that's where I'm at. But they should be based on sound math. And when you start seeing how like AES works, you'll see it. It definitely messes up the message, but it works. Okay? Analyzed by competent experts who has found it to be sound. Okay? I'm working on submitting my idea for my dissertation, for my PhD. And I'm not allowed to use any source off the internet, any source out of a book. Does anyone know why? Oh no. Who writes books?
Authors?
Anybody. How the hell do you know if they're telling you the truth? Who proves this book? Prentice Hall Publishing. And obviously Prentice Hall Publishing is a computer science expert company. No, they're a darn publishing company. Okay? Anybody can write a book. Who puts stuff on the internet?
Everybody.
Everybody and anybody? So what can I use? I have to use referee journals. What referee journals are, you write something, submit it to like the ACM, Association of Computing Machinery, I can't get that right, or the IEEE or something like that. You send it to them. They take it, remove your name, send it out to 6 or more experts in the area, They look at it, see if it makes sense and looks good. They make comments, send it back, and they give it back to you, and you make all the fixes. Then they get it, then you send it again. Now they send it out to 6 different experts who then comment on it. And once everybody's finally happy with it, then you can publish it. That's what something that's a competent expert is all about. It doesn't mean they're going to steal your idea or it's something that's already solved. It's just say, wow, that actually makes sense. The theory behind it is good. That's what we want with our algorithms. We want an algorithm that, why did you multiply this times that? There's actually a reason for it. Okay? Stood the test of time. Now, did the Vigenere cipher stand the test of time? For 300 years, I would say at that time period, that was a darn good cipher. How about the Caesar cipher? Was that a good one? For that time period, yeah, that was a good one. But nowadays, we're a little bit beyond those. So it stands the test of time. DES, RSA, AES, those are all good ones. DES is no longer usable for pretty much anything. But does that mean we don't use it? No, DES is actually still used quite a bit. Because it still takes time to break it. So if that whole timeliness thing we talked about, if you're encrypting something that really, has a very short shelf life, DES is fine. It's good for VPNs and stuff like that. Okay? We will cover each one of these. Okay. Confusion versus diffusion. Since confusion says interceptors should not be able to predict the effects of the ciphertext by changing one character in plaintext. I mentioned that already. So I should not be able to change the third value, increase it by 1 letter, and see a specific character in the ciphertext increased by 1 letter. I want it where if I change 1 character in the plaintext, it changes 87 characters of ciphertext. And we never look at MD5. Okay? We cover it in forensics. Basically, you can take something encrypted with a hash value of MD5, with MD5 hash. Change 1 character and encrypt it again. What's the MD5 look like? Night and day. Every character is different, so there's no way to tell. It says there should be a complex functional relationship between the key pair and the ciphertext. In other words, it should not be 1 character maps to 1 character. You don't want that. Diffusion says changing plaintext affects many parts of the ciphertext. Okay, we want to be able to change 1 and it affects everything. So confusion is we don't want a 1-to-1 mapping pretty much. We don't want that. We don't want to be able to predict what happens when we change character 2 affects character 2. Okay. Diffusion, on the other hand, is we change 1 thing and it changes 87 like MD5. Okay. Information about a single plaintext character is distributed throughout the ciphertext. And that's the thing with AES. I'll tell you guys when you're working on that assignment, it says if you want to send it to me before you're done, that's fine. I'll look at it and tell you if you're on the right track. Because guess what happens if you make an error at the very beginning? The whole blooming thing is wrong. You can go through the whole entire thing and find out you messed up on the first block and then do it all over again. So that's what, do some of it and then send it to me and I'll say, yeah, you're on the right track. And the way I grade AES is pretty neat. If you get it correct, that is. I look at the very end. So if you have the very correct ending, what does that mean?
The whole thing's right.
Everything's correct. So if you guys get 100 on AES, I'm the happy man. If you get anything wrong, my life sucks. Because then I have to go back and find every darn place that something was wrong. All right? All right, stream versus block.
I do that just for shits and giggles.
Stream versus block. I'm thinking this might be another thing we should know about. Okay, stream versus block. Okay, stream, we encrypt 1 letter at a time. It's kind of like, what if as I was typing, and I'm a very slow typist like Roy. I would want a stream cipher. That way, as I type it, it encrypts it. Okay? So, high speed of transformation. In other words, every time I type something, it's transformed instantly, 1 at a time. Low error propagation, because really nothing relies on the previous character. Typing 1 letter, I'm getting 1 letter output. So if I screw up 1 letter, the output's screwed up in 1 letter, but that's it. Okay? Low diffusion, it really doesn't, screwing up 1 letter really doesn't affect anything else. And it is susceptible to malicious insertions. Because if I'm typing slowly, couldn't you just walk over there and hit a couple keys on the keyboard? Sure you could. Now let's talk about block ciphers, okay? Or transposition ciphers we call them. Low speed of transformation. So we got Roy in there typing again, okay? Actually, Roy's not as bad. Caleb, the guy who was there before Roy, literally was the one-finger typist. I'm like, how could you be in this field to be a one-finger typist? But he was quick at it. But still, you can only be so fast with one finger. Okay. So low speed of transformation. So if you type somewhat slow, and Des, for instance, has a 64-bit block, what happens? You have to type 64 things in before you see any output at all. It's kind of like the same as downloading a movie and then watching it or streaming it. Streaming, you hit play, it starts playing instantly. Where some of my videos on D2, it has to download the entire movie. If there's a slow internet connection, what happens? You gotta wait 30 minutes. So that's the real big difference, okay? High error propagation. So if Roy's typing 64 letters before it does anything, then all those are mixed up together. If one of them is wrong, what happens? That whole blooming 64 bits is wrong, okay? High diffusion. Obviously one thing here could really screw up the entire shooting match. It's immune to malicious insertions because we're doing it one block at a time. Now you could stick an entire block in between blocks, but it's not, you can't just stick one letter in there because if you do, it's going to screw up the whole thing. So far so good? Everybody with me? Okay. Breaking encryption. We can have cryptanalysis. There's cipher-only attacks where I know the ciphertext only. Okay. Or known plaintext where I know the plaintext, but I don't know the ciphertext. Or probable plaintext where some of it's known. There's also chosen plaintext where the process is known. I know how you did it. Or chosen ciphertext where the algorithm in the ciphertext is known. So these are just different ways, or different techniques used to break encryption. Okay? Just different ways of doing it.